One of the problems that you often run into when you start looking into functional programming is that you're trying to learn these new concepts, but it's getting tangled up in all this new syntax or these new languages like Scala and Clojure. So my goal in this talk is to focus really just on the ideas and keep it in Java or Java-like languages as much as I can. So most of my examples are in Java and using frameworks in Java. When I can't get Java to do something because it doesn't support something, I try to use Groovy. There are a couple of examples of Clojure and a couple in Scala for unique features of those languages that you just can't really show in other languages, but the real focus of this talk is on the concepts behind functional programming and not syntax. But I want to start with a metaphor, an essay, and a history lesson. Here's the metaphor. Let's say that you're a lumberjack and you're okay. You're the best lumberjack in the entire forest at cutting down trees with an axe. It's stunning how fast you can cut down trees with an axe. Then someone comes along and gives you one of these, but they don't show you how to crank it. And so your first instinct as a great axeman is to take the uncranked chainsaw and swing it against a tree and quickly reach the conclusion, chainsaws are terrible ways to cut down trees. I'm going back to my axe. It feels really good in my hand. I've been using this axe for 10 years. Surely there's no problem that can't be solved with a good axe. And then someone shows you how to crank this, and you can cut down way more trees than you could before. The point of this is that learning a new language is easy. Everybody here has done this multiple times in their career. It's really just a matter of learning new syntax. But learning to think in a different way is really, really hard, and that's what I'm really trying to attack in this session. And my observation here is that functional is more a way of thinking than a particular tool set or particular framework, that you can do more functional coding even in languages like Java that don't natively support some of the building blocks. Here's the essay. This is a terrific essay written by Steve Yagi, who's a well-known blogger. This was written back in 2006. It's called Execution in the Kingdom of Nouns. It's about a mythical kingdom where nouns are first-class citizens and verbs are subjugated slaves. It's so bad in the kingdom of nouns that verbs are not allowed out on the streets by themselves late at night. They actually have a special kind of noun that has no nounness, that does nothing but chaperone verbs around, because who knows what kind of trouble they might get into if you let them off by themselves. Of course, this kingdom I'm talking about is Java, and this insistence that everything be tied to a class, even when it makes no sense for it to be attached to a class. And this makes sense in a lot of cases because things in the real world have properties and they have behavior, and it becomes less and less sensical when you just need to put some behavior around and don't necessarily have to have a class. In fact, they retrofitted Java in 1.1 to add anonymous inner classes, because up until then, you had to create a named class to be able to pass a method around to do some sort of functionality. We're trying to get away from nouns in this talk and focus a little bit more on verbs and stop asking things to do things for us and just do it, or I guess in this case, undo it. So here's the history lesson. This is a poster you can download from O'Reilly's website of the brief history of programming languages. This one only covers about 200 programming languages. There are well over 2,000 programming languages that people have created in the relatively short time we've been doing this. But I want to zoom back to an earlier era for a moment and talk about a really important event. Venkat talked about this event in his keynote on Monday, if you were lucky enough to be here for that. And the event in question is this: Simula 67 in 1967. Does anybody know the significance of this language? Very first object-oriented language. Simula in 1967. In 1971, Smalltalk came along. And in 1983, C++ came along. Now, there's a good argument to be had over drinks as to when object-oriented programming became mainstream. But there was no way it was mainstream before C++. And so you would think that a really obviously good idea like object-oriented programming, as soon as they discovered it, they would have said, oh, this crazy goto thing we're doing now, we should stop this. Clearly, this object thing is way better. But they didn't. It took 15 years before it to even penetrate into people's consciousness, and even more time than that before it became a popular thing. This happens quite often in the computer science worlds, that good discoveries, nobody understands the implications of them till later. Another thing that frequently happens in this world is you have this kind of mainstream technology branch, and you have these branches like academic offshoots, and functional programming was definitely one of those. It's a way to research how to do higher parallelism and cleaner abstractions. And the practical offshoots, things like fourth generation languages in the late 90s. But every once in a while, one of these branches will come back and rejoin the mainstream, and that's exactly where we see functional programming right now. The two most interesting languages on the JVM are Scala and Clojure. .NET ships with F# now, which is a functional programming language. There's interest out in the world in Erlang and Haskell and other functional languages like that. The whole world is going in this direction, and I'm going to show you why the whole world is going in this direction in this talk, and why even if you plan to stay in Java forever, you still need to learn some of these functional concepts because they're coming to you very, very quickly. I wanted to find a good phrase that sums up some of the important lessons of this talk, and I found it via Michael Feathers, the guy who wrote Working with Legacy Code. He said this on Twitter, which is why it's a little bit terse, but he captured a really important concept here. And he says that object orientation makes code understandable by encapsulating moving parts. Think about the things that you know about object-oriented languages, about how scoping works and how visibility works. There are a lot of mechanisms in the language that control who can see a particular piece of state, who can't see it, who can change it, when they can change it, under what conditions they can change it. Those are all moving parts around state management. Functional programming makes code understandable by minimizing moving parts. The theory being, if a developer doesn't have to touch some part to implement it, then there are fewer chances they're going to make a mistake and get something wrong. Excuse me. And I'm going to show you lots of examples of this manifesting itself, of functional programming hiding moving parts from us. But if I want to talk about different coding styles, I need some code, which means I need a problem to solve. And I want to solve a particular problem that some of you may have seen in one of my other talks the other day, but it turns out this is pretty amenable to several different examples I'm going to go through. And it's the problem of number classification. So there's this bit of numerological trivia out in the world over this idea of a perfect number. So the factors of a number are the pairs that when multiplied together yield the number. So 2 and 14 are factors of 28 because 2 and 14, 2 times 14 yields 28. And that's the idea behind this classification scheme, is if you take the sum of the factors of a number and subtract the number, you end up with a number. That's called a perfect number. Another way to say this is sum of the factors of a number is equal to 2 times the number. So for example, 6 is a perfect number because if you take the sum of its factors, it's equal to twice 6. 28 is also a perfect number. You can see its factors there. So is 496. There are not many of these perfect numbers out in the world. This is how you find out which ones are there. And in fact, this is the basis for the classification scheme in general, because some of the factors equals 2 times the number is a perfect number, some of the factors greater than 2 times the number is abundant, and some of the factors less than 2 times the number is deficient. So any whole or positive integer can be classified in one of these 3 buckets. And I want to write some code to solve this problem. The first version I'm going to show you is an imperative version of this code that's based on a chapter from my book, The Productive Program. It is in fact a sample chapter. So if you're curious as to the decision points that led to exactly the shape of this code, I'm really just going to show you the code and not go into the design too much, but I'll talk about the pieces of this code. So this code does classification for me. At the very top of the class, we have the internal member variables. 2 of these are here to make testing easier, and 1 is here so that I can do a lazily initialized sum. I'll show you that in just a second. The constructor initializes the things that need to be initialized. Factors always include 1 in the number, so I can go ahead and initialize those in the constructor for this class. This isFactor method is really kind of the heart of determining factors, because what it says is if a number mod factor is equal to 0, that means factor goes into number with 0 remainder. It is one of the factors, and so this will return true. And so in my calculate factors, what I do is loop from 1 up to the square root of the number, and if it's a factor, I add it. Now let me talk about the square root thing just a second. This is a common optimization for this code. I could loop all the way through the numbers to try to determine factors, but that's very, very inefficient. And you can make the observation that factors always come in pairs. So when I grab 2, and I can also grab 8 if 16 is my target number. And so that means that I really only have to go up as far as the square root of the number, because that is by definition the number times itself, which equals my target number. And so I'm going up to the square root, and then I'm harvesting the factors in pairs. I'm grabbing both the factor and then its symmetrical factor as well. When I add the factors, that makes this a lot more efficient. Here's my sum factor, where I just go through and sum all these factors, just iterating over them and summing them up. Now you'll notice in my is perfect, is abundant, and is deficient, I actually call getSum, and this is lazily initialized. I'm figuring that when people use this, they're going to call more than one classification method in a lot of cases. And so I just want to calculate factors once, so I'm holding on to that internal state with sum by creating a lazy initialized sum. The first time through, you generate the sum, and then every subsequent time, you just return that cached sum value. This is the imperative number classifier. Notice that it has a bit of internal state. That's testability, and so I can do that lazy initialization that I showed you before. This code is very cohesive, and then it's lots of very small methods that just do one thing each. It's very composed in the Kent-Beck composed method style of nice short methods that are very cohesive. It's also very testable. It was actually written as an example of doing test-driven development, so it's very testable, and therefore it is very refactorable as well. My motivation when creating this code was I want to create code that's really easy to test. And that was my primary motivation. But what if I came in with a secondary motivation as well, which is I want to minimize mutable state? Because that's one of the things that you try to get away from in the functional programming world is mutable state. So how could I build this and try to minimize mutable state? We'll build a slightly more functional version, still using Java, no special frameworks or anything like that. And here it is. This is slightly less well factored than my previous code. In fact, the big change is the factors method. This actually encapsulates 3 methods from my other code, but it allows me to create factors entirely within this method and return it as a value, so I don't have to create that as an external member variable. My actual is perfect, is abundant, and is deficient code worked properly, but notice is much, much less efficient this time than it was before. Because now I'm having to calculate factors every time and then calculate sum every time. I was holding those values in intermediate values before, but because I'm minimizing mutable state, I don't have any place to put those, so I have to recalculate them each time. So this is inefficient for multiple classifications because I'm going to have to execute those things over and over. But look at the shape of this code. It has no internal state, and because it has no internal state, there's less need for scoping. I made all these methods public and static rather than private, because there's no reason to make them private anymore. There's nothing I have to hide from the outside world. These are all pure functions now. They rely only on the parameters that come into them. And in fact, this factors method is potentially really useful outside number classification, because if I'm going after prime numbers, I need number factors as well. And so by making it static public, I can now say number classifier.factors of any number and get that value back. So I've actually made reusable functions. And we don't even think about that in the Java world, because normally our finest granularity of reuse is a class, but I'm actually building reusable static functions here. This code is still testable. It's still done TDD, just like the other code was. And it's still refactorable. It is currently less efficient than my imperative code. We'll actually come back in a bit and reclaim that initialization using some functional programming techniques. But for now, at least, it looks like it's doing a little bit more work. So that's our trade-off. We're not storing any internal state, but we're having to do a little bit more work to recreate that state when we need it. But I think this goes back to support my contention from earlier that functional is more a way of thinking than a particular tool set, and you can write more functional-ish code in Java with a little bit of effort. One of the things that you'll find as you start delving into functional programming is that there's lots and lots of information out there. And some of it is very academic and very fascinating, but not terribly practical. So what I want to do is pick just a few topics in the functional programming world and show how they impact or have some reflection on us in the JVM world. So I'll talk about a few of these concepts and show you examples of a few of them. The first of these are first-class higher order functions. This is what we're finally going to get in Java 8 with lambdas. These are basically interchangeable terms. One is a computer science term, another is a mathematics term. The basic idea, though, is portable functionality. You can pass functions as parameters. They can be return values. You can treat them like first-class citizens in the language. We just saw some examples of pure functions, which are functions that take no side effects external to themselves. They accept only parameters and have no side effects outside their parameter list and their return value. Recursion is something that we don't talk about much in the JVM because the JVM is not well optimized for it, but I'll show you an interesting example of recursion and why it is preferred as an iteration technique in functional programming languages. And finally, strict evaluation is a bit of an academic concept, but it leads us to some really cool places in the functional world around laziness and lazy data structures and infinite collections and things like that. So let's talk about a few of these concepts. And the first of these I'll talk about are higher order functions. This is basically the mathematics definition of functions that can either take other functions as arguments or return them as results. We have long needed this facility in Java, and because we have lacked it, we have paved over the shortcoming with a design pattern. So let me show you what I mean by that. So this code is actually the target of a refactoring exercise I do in one of my other talks, but what it does is not that important. The observation when I get to this point is that, oh, if I knock out these two really specific lines of code, I basically have a nice template for doing persistent data persistence with guards on it. And so I want to be able to reuse that at some point in the future. So how do you do that in the Java world? We use the command design pattern. So what I'll do is modify this using the command design pattern and create this. I create wrap-in transaction that takes in a command, it executes it at the critical spot, and now my add order from, I can do wrap-in transaction, create a new command, and have the execute method do my two little pieces of work there. This, though, is really just portable functionality. This is a cry for help for a higher order function. Because that's all we really need here is a higher order function, and yet we have to create a class and a method to be able to pass that around in Java. So when we get higher order function, we get lambda blocks, this kind of code goes away. In fact, the command design pattern is deprecated when you have higher order functions in your language. You don't need the command design pattern anymore. It's a band-aid for the lack of higher order functions. And in fact, if you look at this same code in a more modern dialect of Java like Groovy, you do exactly that. Anything in curly braces in Groovy is a code block. I'm doing the exact same here, following the exact same design pattern here, but all the class definition is invisible here because I'm using a higher order function as the way I'm passing that behavior into that other method. So this is really convenient, but this code block in Groovy is not just a code block, it's also a closure. And that's the other thing that we get with lambdas. And I want to spend just a minute and talk about what's so cool about closures and why do we want these things so badly. So I wanted to put together the shortest code example I could of what's really cool about closures. So let's see how well I did. This is in Groovy because Java doesn't support this concept yet. So here's a Groovy function called makeCounter. It defines a local variable called veryLocalVariable and sets it equal to 0. And then it returns a code block. I don't care what it does for the moment, just realize that this returns a code block. So when I say C1 is equal to makeCounter, C1 is now pointing to one of those code blocks. When I say C1, open and close parens, I'm executing that code block. So what does that code block do when I execute it? It says very local variable equal to very local variable plus 1. And then in Groovy, the return of a code block is the last line unless there's an explicit return. And so this is going to return the value of very local variable. And so the value here, if I was curious, is 1, and there it's 2, and there it's 3. And then I go and say C2 is equal to make counter. Behind the scenes, what's happening there is that I have two instances of this code block now. One pointed to by C1 and the other pointed to by C2. But when I come along now at the bottom and say, okay, give me the current value of C1 and the current value of C2, I get 4 for C1 and 1 for C2. Because here's what's happened. Notice that the reason this won't work in Java is because this local variable up here is out of scope by the time you hit this closed curly brace. It would reset the value of that local variable every time you call this function. But this is what's so special and magical about a closure. Because what happens when a closure block is when you instantiate the enclosure block, it looks at the things in its environment that it's referencing. It holds on to those references for the life of the closure block. And so C1 has its own version of very local variable, and C2 has its own version of it. And it's keeping its value between these method invocations, allowing me to sum these values up. This is the thing that's unique about Clojure, is that it creates an enclosed environment around all the things that are present and in scope when you spin up the Clojure block. And then those things are kept alive by that Clojure block until it gets garbage collected, and then all those references it's holding on to get garbage collected as well. That's why you have to have closures to do some of the things that you do in collections APIs. But this is a great example of eliminating moving parts. I don't have to keep track of that incrementing value anymore because the Clojure block is keeping track of that for me. I'd much rather let the runtime track that and force me to have to track that value. And in fact, that brings up kind of an interesting point, that I would rather let the language manage that state for me, rather than having to write handcrafted code to do that. Easier than Java does, because Java has some flaws around the way that it does concurrency. Back in the early 1980s, when I was in university, we used to use a system called Pecan Pascal. The cool thing about Pecan Pascal was you could write Pascal programs that would run on the IBM PC and the Apple II. And it was really cool. It was using this technology they called bytecode. So they wrote this thing called a virtual machine that ran on the PC and the Apple II, and it was as slow as possible. It was crazy slow. It was almost unusable even for college projects. Because back in 1983, we didn't have enough horsepower to run virtual machines and do bytecode and do that level of abstraction in the hardware. But 10 years later, Java came along, and we did have enough resources to do that. And now that I've been working in a garbage collected language like Java, I never want to go back to a non-garbage collected language again. Been there, done that, got the t-shirt, don't want to go back, because it sucked. I hated chasing down pointer problems. You know what? That's not the best use of my time at an enterprise writing software, is chasing down pointer problems. I should be solving much higher level abstraction problems, and that's exactly what Java allowed us to do. We don't have to worry about chasing down memory pointers right now. But what's happened over the last few decades is we now have an enormous amount of overhead, and that's exactly what some of these languages are doing, is using some of that extra overhead to take away more busy work for us, like concurrency. Clojure has some brilliant concurrency stuff. They do for concurrency what Java did for garbage collection. Meaning you can write high-performance, multi-threaded applications in Clojure and never once worry about threads conflicting with one another, because the language handles that problem, not you as the developer. This is why you should care about functional programming, even if you don't care anything about Scala or Clojure, because every language you're using is adding these features as quickly as possible, because our runtimes are now robust enough to allow us to operate this higher level of abstraction. So over time, we're seeding more and more stuff to our languages and runtimes, even things like test. There's some really cool specification-based testing frameworks out in the world. Higher order functions and first-class functions are essentially synonyms with one another. This is typically the computer science term, whereas higher order functions is typically the mathematics term. But these are functions that can appear anywhere any other language construct can appear. And I want to start talking about the use of this and some design philosophies. In the object-oriented world, the way that you solve problems is by creating networks of classes that send messages to one another. If you look at the classic design book in the object-oriented world, it's design patterns, elements of reusable object-oriented software. Every single example in that book has a class diagram. Because that's how you solve problems in object-oriented systems, is a system of classes. That's not the way they try to build abstractions in the functional programming world. Because when you're building a new abstraction for every problem you have, you're almost building a mini language. So you don't have any methods that already work against your customer class. So you have to write methods on your customer class that understand that context. What the functional programming world tries to do is focus on a few key data structures and build really hyper-optimized machinery for working on those data structures. And what you do is take data plus higher order functions that plug into the machinery to customize what it does, pass that packet into the machinery, and then it does transformations and other things for you, and it comes out the other side. So in the functional programming world, they actually focus on a few core data structures, and let's build some really, really advanced functionality into those manipulation of those core data structures. So for example, in the Java world, how many XML frameworks are there out in the world? There's got to be at least a dozen popular ones out in the world, and every one of them has a completely different API. It's the one written by whoever's writing that XML framework. In the Clojure world, the way that you deal with XML is the very first thing you do is mash it into this nested map structure that's really well known in the Clojure world. In fact, the XML parser piece of Clojure mashes that down into maps, and now you have really good tools in Clojure for dealing with maps. Really hyper-optimized ways of getting to things in maps, etc. And so the attempt in Clojure is, let's get this mashed into a shape we already know, and then we'll work on it, rather than building unique shapes for everything. Let's look at some examples of this kind of higher abstraction of power. And I want to point you to a framework called Functional Java. This is a framework that's been around for several years. It's in production in a lot of places. It's in its at least second major release. This is an attempt to add functional programming concepts to Java without changing the Java syntax. So what they're doing is cheating a little bit and using generics and anonymous inner classes to stand in for higher order functions. So we don't have closures and some nice things like that, but we do have some of these abstractions that come from the functional programming world. The nice thing about functional Java is that this work is a single jar file. It works with any JDK 1.5 or greater. This does not download an entire Maven's worth of jar files to your machine to be able to use it. So it's a single jar file that you can use. So what I want to do is take my number classification example and write it in functional Java and see how it's different. And here it is. So let's look at what's different here. The first method we'll look at that's different is sum. So here's my sum method now. Sum, my factors, where I say factors.foldLeft add comma 0. Now how in the world is that doing a sum? Well, first of all, notice this is not a Java util list. This is a functional Java list, because Java util list doesn't have a fold left on it. And that add thing is a little bit confusing as well. That's actually something that's built into functional Java as well. That is the combiner function that I'm going to use. You can put your own there. I'll show you what that looks like in just a second. Here's the idea of a fold. So I have a list of numbers, and I want to convert this into a single value. What I'm going to do is take the second element and fold it in on top of the first element. And I need to use some operation for that fold. I think I'm going to use add as the operation. And so what's going to happen is I'm going to take the second element and fold it in on the first one and add them. Then I'm going to take the new second element and fold it in on the first one using add. I'm going to do that for each element until when I'm done, I have the sum of the list. This is known as a fold operation, or it's also called reduce in some functional languages. I'm doing this transformation from a list down to a single or smaller list. It doesn't have to be a single value. It could be a smaller list by providing a combination function between those guys. This, of course, has to be kind of bolted onto Java. So this is the functional Java, and you'll notice they've already predefined a few of these helper methods for you. In languages where this is a natural thing, it's not bolted on. So this is the same code in Clojure. Clojure is a list, so you kind of read inside out. This defines a function called SumFactors that takes number as a parameter. Factors of number returns the list of all my factors. So this says reduce, take the factors of number as the list of numbers I want to reduce, and then this is any method in Clojure that accepts two parameters and returns a single value. So in Clojure, operators are just methods with funny names. This happens to be a method that takes two values and returns a single value. This can actually be any method that takes two values and returns a single value, and it'll reduce that list based on what that method is. This doesn't just work on numbers. This can work on any structure. It can work on strings, any sort of reduction function where you supply two parameters and it can return a single result you can do a reduce on. This is a really good example of a really common thing in the functional programming world is you think about results rather than steps. Rather than thinking about iterating over this collection, you think about what sort of transformation do I need to apply to that collection, because I know I want to transform value out of it. A sum of a list is really just a transformation of taking all the elements and combining them down to a single element. That's just a transformation. There's another place where I was doing iteration in my imperative version. Let's see if we can figure out how to do that without iteration. And it was the place that discovered factors for me. So let's say I'm trying to determine the factors of 12. How can I do that without iterating all the values to 12? Well, the first thing you could do is make an observation that it's going to be some of these numbers, but probably not all of them. Here are all the possible factors of 12. And it is in fact going to be a subset of those numbers, which suggests a filtering operation, which is exactly what I'm going to do. This gets the factors of, this returns a range of numbers from 1 to number plus 1, because ranges are non-inclusive in functional Java, then dot filter. Now, normally, and in Java 8, this would be a higher order function that you're passing to filter. It's going to be a code block that executes against every element, returns true or false as to whether included or not. But we don't have higher order functions in Java yet. So what functional Java does is cheat with some generics. And so you create a new F class that expects an integer parameter and a Boolean result. And then you create an F method that does that with a Boolean return and an integer as a value or as a parameter. And you'll notice what I'm calling inside that method is my isFactor method that I wrote earlier that determines is this number a factor or not. And so once I run this code, what I'll be left with is a list containing only the numbers in red, because I will have filtered the non-factors out of my list. Now, I have a question for you. Is this code more or less efficient than the handwritten imperative code I showed you first? This is in fact much less efficient so far, because I'm touching every number in trying to determine if these numbers are factors or not. So this is less efficient so far. I'll come back in just a bit and optimize this using functional Java and get the same kind of optimization back. But notice for now, for the simple version of this, this is not quite as optimized as the hand-tuned imperative version. And here are the three main methods that were affected by my transition to functional Java. isFactor, of course, didn't change. There's my factors of, and then there's my sum. Good example of thinking about results rather than about steps. And one of the other functional concepts I was talking about is this idea of pure functions, which are functions that have no memory or I/O side effects outside themselves. They rely only on their parameters. And purity has some really, really nice characteristics. Because for pure functions, if the result isn't used, the runtime can actually just remove the function entirely, because nobody's going to use it for anything. Your runtime can also execute these pure functions in parallel, or it can change the order of them if it needs to. because they have no side effects. And up until recently, these were the primary benefits of having pure functions. And these were mostly benefits that the runtime manifested for you, figuring out how to optimize away dead code and stuff like that. But there's an observation that can be made about pure functions. For example, math.cosine in the Java libraries is a pure function. Now, when I call math.cosine today, do I have to worry that tomorrow when I call math cosine, I might get a different value if I send it the same parameter? I'd better not. If I call math of cosine for 89, I'd better get the exact same value back every single time. What that suggests is that for a pure function, a particular method call with a fixed parameter yields a constant result. And that we can take advantage of using a language feature called memoization. Let me show you how this works. This is a groovy version of my number classifier written using the functional pieces in Groovy, because Groovy has quite a number of functional constructs in it. My isFactor method hasn't changed. My factors of method, I can do ranges here by saying one ... number. That gives me the range of numbers. Find all, here's the filtering mechanism in Groovy. It takes a code block as the parameter, and notice my code block calls my isFactor method. There's a little bit of grooviness in here. Find all actually takes a single parameter, which is the value you want to send in. But if you have a single parameter, you can just substitute it with it rather than creating the parameter and then calling the parameter. So that's where it came from. My sum of factors takes factors of number and then .inject. Inject is Groovy's version of reduce or fold. 0 is the seed value, and then notice I'm passing in a code block that accepts two parameters and returns a single value. That's exactly what sum does as a reduce. And then finally I have is perfect, is abundant, and is deficient. So let's say that I decide at some point that I would like to cache the sum, kind of like I did in the first example. So this is easy enough. I can create a sum cache, which is a map, initialize it in constructor. And now in my sum of factors, if the sum cache contains the key, return that. Otherwise, calculate the sum, put it in the cache, and then return it. This is very familiar to many of you. You've probably written some handwritten caching code like this at some point in the past. There's no great mystery or surprise here, except that it's completely not needed anymore. Because Groovy has introduced this idea of memoization. If you have a pure function, and my sum of factors is a pure function, I can take that function definition and then say sum of factors is equal to sum factors dot memoize, and I am all done. The runtime will now cache the returns of this function for me and keep track of them for me. I don't have to write any of that code anymore. And in fact, Groovy has methods for memoize at least this many elements, memoize at most this many elements. There are some methods where you can fine-tune the way that Groovy is keeping its cache internally. This is a fantastic example of this idea of new and different tools and ways to solve things. Because this is a bunch of code you don't have to write. In fact, remember, when I was talking about my slightly more functional version of Java, I was lamenting the fact that we had lost the optimization on my is perfect, is abundant, and is deficient. But sum up there is a pure function, so if Java had memoization, I would have the exact same performance here, and yet I don't have to hand write the lazy initialization anymore. The runtime handles that for me. That's a great example of hiding moving parts from me. Because if I don't have to hand write a cache, there's no way I can mess up the handwritten cache. And the stuff that's written in Groovy is way more efficient than anything that you can write because they've written it at the language level, not at the developer level. So they have access to private data structures and other things that you don't normally have access to. It's a great example of new ways to attack problems. So next I want to talk a second about recursion, which has always been a little bit of a second-class citizen on the JVM because it doesn't do proper tail recursion, but it's getting a little bit better, and in fact there's effort in the JVM to fix that problem, and in fact the languages that rely on this a lot like Scala and Clojure have already fixed this problem internally. But I want to talk about this as a concept for just a second. So here's an example in Groovy of iterating a list. So you pass in a list. This is still doing classic iteration, even though I'm using .each. This is still basically going through each element. In fact, if I want the index values here, there's an each with index in Groovy as well. But notice that this assumes a certain perspective on lists. And that perspective on lists is that a list is a contiguous chunk of memory that's indexed. But we know underneath it's not that at all. And so there's a different perspective on list, which is this idea that a list is really its first value and then all the rest of the values, which is just another list. So the idea in recursion, of course, is do something to the first one and then do the same thing to whatever's left, which will pull off the first one and do to whatever's left. And you chew through the collection like that without ever directly caring about what its index number is. Notice that Groovy shares this perspective on lists with us. Because in Groovy, I can say recursive list by saying if the size is 0, then return. Otherwise, print out the list, the head of the list, and then recurse on the tail. So Groovy already has a head method that returns the top item and a tail method that returns the sublist. Let's think about filtering. I want to filter a list. So to do that imperatively, I get a new list, initialize it, and now for each element in the list, if it matches the criteria that I passed in as a higher order function, then add this element to the new list and then return it. My mod by 2 code block says give me something that is divisible by 2. And so I can now say L is equal to the numbers 1 through 20 filtered so that I only get the even ones. Let's do the same thing with recursion. I'm going to take in a filter and my criteria I've changed to P, which suggests it is a predicate, which is something that returns true or false. And if my list size is 0, then just return the list. Otherwise, if the predicate of my head is true, then it needs to be on the filtered list, so I'll return an empty list, which makes sure that this is always a list from a type standpoint, plus the head, plus the filtered tail. Otherwise, I'll just return the filtered tail. When you look at these two side by side, what's the real difference between these two, between the imperative and the functional? The real difference is that new list guy. Where is that new list guy on the recursive version of this code? It's not there. The runtime is managing new list for you. Because notice every exit from filter is return. So new list is actually being built up on the stack, not by some variable that you have to touch and you have to update and you could potentially make some mistakes for. This is one of the reasons that they like recursion more than iteration, because you basically just do the same thing over and over and then let the runtime manage the intermediate values and state for you. This is a great example of eliminating moving parts. Recursion actually gets rid of the moving parts of that index. Of course, we can't do this without caution on Java because it's not wired for this. The languages that are wired for this, this is a perfectly reasonable thing to do. In fact, here's the exact same example written in Scala. There's a filter method that takes in a list of integers and a predicate, which is a method that takes an integer and returns a Boolean. If the list is empty, then return the list. Otherwise, if the predicate of head is true, then construct a new list with the head and the filtered tail on the end. Otherwise, return the filtered tail. So this is the way to do this. This actually is from the Scala documentation as a way to show how to filter over collections using recursion. A great example of thinking about the results, not the steps required to get to those results. Which I've mostly been talking about as a good thing. But what about the times when you want to think about the steps? When you want to get in there and monkey around with something like optimization or something like that, you can still do that, but it's new, different tools to allow you to do that. So if you remember, in my imperative number classifier, one of the cool things I had in there was this optimization, the square root optimization, so that it did as little work as possible, trying to determine my factors. How can I optimize that in functional Java using the same kind of algorithm? Well, I can. It looks like this. So now what I want to do is say, create an intermediate value called factors, which is going to be the range from 1 up into the rounded square root plus 1. Remember, ranges in functional Java are non-inclusive. Then dot filter. I'm going to filter all these guys and get all the factors up to the square root. So there's my number list. This is going to give me all the values up to the square root. Now I'm going to return factors.append. So I'm going to append onto this list another list. What I'm going to append on it is factors.map. That's a transformation we haven't seen before. What map does is take every element in the collection and apply the higher order function to it, yielding a new transform collection. So what higher order function am I applying to this guy? I'm basically taking this little anonymized thing and I'm basically appending the symmetrical factor onto the top of them here. So I start with my factors below the square root. This is actually going to build the factors above the square root for me and append them onto that list. There's one last little line of code here called nub at the bottom. The reason for that is that functional Java primarily operates on lists, and I needed this as a set to make sure that I don't have, there's an edge case here for whole number square roots. Functional programming does not eliminate the need for unit testing, because that's how you find those kind of edge cases, is a whole number square root. What nub does is convert this into a set and gets rid of any duplicate items that are in there, which is that whole number square root little issue. In the perfect world, I would do all these operations directly on set, but functional Java has most of these methods on list, but it makes it easy to transfer back and forth between set and list. So thinking about results rather than about the steps. The last big subject I'm going to talk about is probably one of the reasons you came here, and that is functional programming's unique take on concurrency. And I'll talk about two different takes on concurrency here, one from the Clojure world and one from the Scala world, both of which is making an attempt to simplify concurrency on the JVM. There's a terrific keynote that Rich Hickey did at Strange Loop a couple of years ago now called Simple Made Easy, and in it he describes many of the design philosophies that he created in Clojure. And one of the really cool things that he talks about in that keynote is what makes threading so hard in Java. What's the core thing that makes threading so ridiculously hard in Java? It turns out that it's variables. Because variables were created in Java before they ever thought about making a multi-threaded language. And they made a bunch of really poisonous assumptions around variables that made it really hard to do threading when it came time to do threading. Because variables assume one thread of control and one timeline. They're not atomic. They don't compose with other variables. It's really hard to get good transactionality around setting a disparate set of variable values. They have subtle visibility rules that you have to learn and adhere to. And with the concurrency primitives in Java, which were very much bolted on after the fact, you were pretty much in the lock and pray kind of world. Rich figured out what's making this so tough, because when they decided on the implementation of variables in Java, they gave it too many responsibilities, because variables are responsible for the identity of the thing and the value at a particular point in time. So those are basically three jobs that variables are doing. Anytime you have one mechanism handling multiple jobs, that's kind of a bad idea. And so Clojure figured out how to fix this. The way that Clojure fixed this was by adding another level of indirection here. So in the Clojure world, everything is immutable, except one thing, which is a reference. A reference points to an identity that never changes. An identity will point to a value at some point in time and maybe a new value at a different point in time. That's its state. It's whenever you capture the snapshot. That's what that identity's value is going to be at a state time, but identity never changes over time. And what Clojure has done is said, I'm going to take control of this assignment, and by doing that, I will solve all your concurrency problems. Because now you can write perfectly performant thread-safe code in Clojure and never once worry about a synchronized block or locking or any of those other primitive things that you have to worry about in the Java world. The way that it does this is how it happens diagrammatically. You can think of this dotted box here as a reference over time, and it has a particular value at a point in time. You apply a pure function to it, and it now points to a new immutable value. At some point, an observer or another program or somebody like that is going to look at that. That is going to be its state at a point in time, which is the value being pointed to by the entity. This is what Clojure calls the atomic succession model, to make sure that everything that you apply to this always happens correctly and always happens transactionally. The other cool thing that Clojure has is this concept of software transactional memory, where you can actually say these two variables need to coordinate together, so I want to make sure that both these variables get set or neither of them get set. These are transactions just like you're used to database transactions. These are ACI but not D. They're atomic, consistent, and isolated but not durable. This is software transactional memory, not disk or file system. But it has all the same characteristics of transactional systems that you've worked with before, but it's built in at the language level, not at the framework or any other level like that. This is a core piece of how the language works. The syntax for this is actually disappointingly simple after I've shown you all this cool mechanism. This is the way that it works. Here's how you create a reference to something. I want to create a new variable called messages, and it is going to be a reference that will start out as an empty list, so that's going to be an empty array. If I want to find out what's in ref, I can call this dref on it to see what's in it. There's syntactic sugar in Clojure. The @ symbol is the same as calling the dref function, and that gives me the value the reference is pointing to. Now when I want to alter a message, I call an alter function, give it the record, an update function, and whatever arguments it requires. And what this does is move the identity from pointing to the old value into pointing to the new value within a transaction. And here's what this looks like syntactically. I have a method here called addMessage that takes in the message that I want to add. It says alter messages, which is my reference, conjoin this new message onto the end of it. So that's basically saying tag this new message onto the end of my messages. But notice that do sync there. That's what does this inside a transaction. In fact, if you try to execute this code without the do sync there, it will fail, because Clojure refuses to mutate things outside of a transaction. But because of that, you can write perfectly performant, high-performance, thread-safe code and never worry about it. Clojure will automatically do retries for you. It has some sophisticated stuff built in, so it'll do barging. If something's retried a bunch of times, it'll actually bump the priority on that thing and make sure to try to get it to execute. It'll eventually fail if it can't. So it's a transaction mechanism just like you're used to in things like database systems. But it's kind of notable that there are really only two commercial-grade STM implementations in the world, as far as I know. Haskell and Clojure. And not surprisingly, both those languages want things to be as immutable as possible. The .NET guys tried a few years ago to build STM on top of .NET and abandoned the effort, because trying to do STM in an environment that allows free mutation is impossible to get to work. It's just too complicated to deal with. And so immutability is really the key as to why this is possible in languages like Clojure and Haskell. Scala also hides many of the messy details of threading away from you, but in a different API, in an actors API. So notice one of the approaches I could take to optimize my perfect number finder is to say, well, determining the factors for a number has no impact on whether I'm determining the factors for another number. Now, if I have CPUs, I can actually split that work up across multiple CPUs. And that's a good use for actors. So here's a parallel perfect number finder in Scala. I'll create my isPerfect method, create a number of partitions based on some criteria, like number of cores I have or something like that. And now I can come down here and create a bunch of actors. For the number of partitions I have, there's the lower and the upper. That gives me, so if my number is 16, I'm saying, okay, first CPU, you handle the numbers 1 through 4. Second CPU, you handle 5 through 8, etc. And then I spawn a bunch of actors for each one of these guys. This actor owns a partial sum, and it goes from the lower to the upper, and it looks to see if that candidate is within, it matches my algorithm. This is basically that is factor method that we saw before, just exploded in line. If that is true, then add this value to partial sum. When I'm done with that for loop, then send this message back to who called me. This is the message passing a la Erlang. This is how the actor sends a message back to who called him. And so now at the bottom, I know the number of responses I'm expecting. So while I still have responses out there, receive, that'll grab that partial sum, and I can decrement my partial or my responses expected, add my partial sum to my sum. When all the responses are in, I check to see if sum is equal to 2 times candidate, which is the definition of a perfect number, and that will return true or false as to whether that's a perfect number or not. So Scala is giving you a way to easily spawn threads by creating this actor concept. And again, you don't have to worry about the intimate details of synchronized blocks and all those other details because the language is managing all those things for you. Another great example, in fact, of eliminating moving parts, all those moving parts that are required to do threading correctly in Java. So I want to leave you with a little bit of advice that you can take back to your office with you. One of the things that you want to start tiptoeing into a little bit is immutability over state transitions. Now, immutability is tough in Java because it was never designed for that. Groovy actually has some nice annotations that make things immutable, so you can make immutable classes there. Here's a fun experiment to try. So when you go back to your office, go and do a global search and replace in your IDE and replace the word private with private final. And then try to compile your code. You'll get what I call your mutability score, which is all the places you're mutating stuff. And most of those are probably legitimate, but some of them may be not. So start thinking about, can I make more things immutable? Notice that you never have to worry about strings in Java. You don't have to worry about them in threads. You don't have to worry about them in any of the places, about equality or any of that other stuff. That's because strings are immutable, and they're immutable on purpose because it makes everything around them a lot simpler. So we need to start embracing immutability a bit more. Start thinking about results over steps. We're going to get lambda blocks in Java soon, but when you start looking at problems that require iteration, think about, if this wasn't iteration and some sort of transformation, what might that look like? Try to think about composition over structure. I showed you this example before. The object-oriented world, the way that they try to achieve reuse is through networks of classes. And if you find some reusable code, you pull it off to the side and package it up, and that's how you reuse that code in the Java world, structural reuse. In the functional programming world, we're much more interested in functional reuse and this idea of core data structures and optimized operations on core data structures. And we saw 3 of these catamorphisms, these transformations. We saw the fold, reduce kind of catamorphism that takes it from multiple values down to a single value. We saw the filtering transformation that takes a big list and turns it into a smaller list. And we saw the mapping operation that takes one list and transforms it into another list by applying a high order function to each one of the elements along the way. These are core abstractions in the functional programming world. Every functional programming language and framework has these concepts in them. They may be named slightly differently, but they all have the concepts there, and all these concepts are going to be there with Lambda blocks in Java 8 as well. And start thinking about declarative over imperative code. This whole idea of results over steps really leads you to more declarative code. And that's really the benefit of operating at these higher levels of abstraction and getting away from iteration, because when you're iterating over something, you're necessarily mired in the small details. When you're thinking about transformations, it's actually easier to think at a higher level of what these transformations are and not get sunk down into the details so much. So to summarize, functional thinking are new ways of thinking about old problems. Gradually cede more and more control to languages and runtimes. Don't resist that. Embrace it. Start using these features as soon as they come about. There's some immediately beneficial starting steps like embracing immutability as a first-class citizen. Think about transformations as opposed to iteration. You're aligning yourself with language trends. Every single language is becoming more functional at a really, really fast rate. Every language you can think of now is either becoming more functional or has really good functional parts in it. And these new capabilities give you new ways of thinking about problems that maybe you didn't have before. And it may encourage you to attack problems that seem too complex to attack in previous times. So if you want more info on this, I actually have an article series that I produced on IBM Developer Works. There are 20 installments of this. You're welcome to read and get more info about this. In fact, I haven't even put it up on a slide yet. I just filmed a 4-hour version of this talk for O'Reilly that's streaming as video. If you want more info on this, actually a much expanded version of this. There's the written version and the video version. I'm just about out of time. I'm close enough to time. I don't want to cut into any of Scott's time. So if you have any questions, I'll be happy to answer them later. I'll be here for the rest of the day. Thanks very much for coming, and I hope you enjoyed it.